Data quality is an important consideration for any machine learning workflow. If we feed poor quality data into an algorithm, we could degrade the results that are generated from it, and thereby we impact the future decisions we make based on those results. Hey guys, I'm Andy, and if you already knew that, then welcome back to the channel. In today's video, I'm going to share with you a presentation based on my paper that I published last year, which focuses on the data quality considerations for machine learning models within petrophysics. This paper was presented last year at the Society for Petrophysicists and Wildlog Analysts, or the SPWLA for short. Within the paper, I touched on a number of topics, including the basics of what machine learning is, the types of machine learning models, and also what we should consider when we're looking at data quality before feeding in well-logged data to machine learning models. Anyone who has worked with well-logged data will understand that that data can be affected by a variety of issues that go on within the borehole and also within the tools themselves. We could have washout in the borehole, which changes the readings that we receive at the tools, and we could also have tool and sensor failure, which may show up as outliers or erratic data. If poor quality data is not identified at an early stage during the machine learning workflow or the petrophysical workflow, then we could generate incorrect results with our equations and with the algorithms that we choose to use. And therefore, any decisions that we base on those results could have financial and safety consequences. Also within the paper, I look at a number of case studies using popular machine learning algorithms and some common data issues, including missing data, which is actually one of the most common issues that we face, and also looking at the impact of noise on the prediction of a random forest algorithm. So let's get started. Before we move on to discussing data quality, we first need to cover what machine learning actually is. And machine learning is a branch of artificial intelligence and computer science that focuses on using data and algorithms to imitate the way that humans learn. And the definition used here is a simple one that I've come across many times, and it is the ability for machines to learn from data without being explicitly programmed to do so. This means we initially train the models with the data, and any time new data is presented to the model, it should be able to handle that data and apply the model to get the desired results. In other words, the algorithm should be able to generalize to new data. Artificial intelligence, or AI, is a vast discipline that covers computer vision, robotics, expert systems, speech processing, machine learning, and many other related subdivisions. According to the former Dean of the School of Computer Science at Carnegie Mellon University, AI is the science and engineering of making computers behave in ways that until recently we thought required human-level intelligence. We then have machine learning, which we've discussed in the previous slide, and then a further subdivision of machine learning is deep learning. And this focuses on the use of deep or multi-layered neural networks to gain deeper insights into the data and also make better and more accurate predictions, assuming that the model is accurate and robust. Another term that you may have heard of in recent years is big data, and this refers to the large volumes of data that is generated by humans, machines, and tools that is often too large or complex to be processed using traditional computing technologies. Instead, it requires new and innovative technologies to gather, manage, and process that data. And big data can feed into AI, machine learning, and deep learning to provide a greater understanding and allow us to gain better insights from that data. So how does machine learning compare with traditional programming? Well, in traditional programming, we create a model or a set of instructions, typically based on if-then-else logic, and then we apply it to the data to get our required result or answers. And due to the complexity of the data and its variation, conventional programming may not be suitable for our needs. Machine learning, on the other hand, is where we provide the data alongside the answers, and these are then used by the machine learning algorithm to derive the final model or set of rules, which can then be applied to new data to make predictions and allow us to gain deeper insights about our data. So now that we have covered what machine learning is, we can move on to well-logged data quality. If you want to find out more on machine learning and how it can be used in petrophysics, then be sure to check out the video on my channel called Applications of Machine Learning to Petrophysics. And in that video I cover a number of applications where machine learning can help us improve our workflows. But before we discuss data quality and its impact on well-logged data, we first must define what data quality is, and there are several definitions out there. Within the literature, data quality is often defined as fitness for use for a specific purpose. For example, achieving specific business goals, making effective and informed decisions, or planning the future of operations within a well or within a field. In ISO 9000 2015 edition, quality is defined as the degree to which a set of inherent characteristics of an object fulfills requirements, where inherent refers to a property that exists within an object as opposed to being assigned to it. In the Norwegian Standard 5801, data quality can be defined as conformance with specified requirements. Often publications refer to data quality as a relative property of the data, whereas it should be an absolute. So a number of publications and organisations have referenced key characteristics as a way to measure relative data quality, and most publications are in agreement with 6 key dimensions. First is completeness. Is all of the required data present? Data should be as complete as possible for the given task and can be measured between 0 and 100%. Accuracy. Does the acquired data reflect reality? In our case, the well logs provide an accurate representation of the subsurface. Timeliness. Is the data up to date? When working with data, we should be working on the most up-to-date version of the data as possible. If the data is out of date, then any decisions that we make based on that data could be incorrect. Then we have consistency. Is the data consistent? When comparing the same data across multiple storage locations, software packages and file formats, that data should be consistent. For example, if we take a density log from a log plot, it should be the same as the one in the dlist file and in the last file. If they are not the same, then that is classed as inconsistent, and then we would need to investigate it further. Then we have validity. Is the data valid? The data should fit within predefined expectations and limits. For example, if we have a measurement such as bulk density, where we expect values generally between 1.5 grams per cc and 3 grams per cc, but we suddenly get values that are 7 grams per cc, 42 grams per cc, these values are considered invalid and could also be considered as outliers and therefore requires further investigation. And finally, we have uniqueness. Are all of the features within the data set unique? Duplication of logging curves within databases and across file formats is a very common issue within our industry. Ideally, we should be working with just one version of each measurement. So out of these 6 dimensions, accuracy, completeness and consistency are the most problematic when working with well log data. Following on from the dimensions, we can look at specific issues within well log data that can cause us concern. The first and probably the most common issue that we face is missing data. This can occur as individual missing data points or entire missing measurements. An example can be seen here to the right where DT and DTS are entirely missing from this well. Data can be missing for a number of reasons, including data vintage, tool and sensor failure, logging speed issues, stick and pull, borehole environmental issues, improper data management and casing effects. Missing data can be infilled, however it should be done with caution as it can lead to a skewing of the results and introduce bias into the data. Next, we have outliers. Outliers are anomalous data points that do not fit within the normal or expected statistical distribution of the dataset. And outliers can occur due to measurement errors, tool sensor problems, unexpected events or unexpected geology, and changes in the borehole environment. Outliers can be identified using a number of statistical and visual techniques such as box plots, cross plots, and calculating a z-score to see how far a point is away from the mean of the data, and the removal or replacement of outliers can be controversial, so it's essential that you understand why that point is an outlier and whether anything can be done to rectify that. Inconsistencies within the data is a common issue across the industry, with many of the same measurements having multiple naming conventions depending on the data source. The correct data and types need to be identified and dealt with appropriately, otherwise confusion can occur when selecting the appropriate inputs to the model. Data normalisation. It is commonly assumed that stratigraphic units within neighbouring wells should share similar properties and therefore similar log responses. Therefore, if there are any discrepancies even after applying borehole corrections, there could be other factors at work such as differences in tool and sensor technology. Normalisation generally forms part of a petrophysical interpretation, however it can be considered controversial as some people prefer to avoid doing it. And finally, we have depth alignment. Depth is a critical measurement for the successful development of an asset. If the data is not at a consistent depth, when building machine learning models, the algorithm will use incorrect data to build relationships with the target feature. Depth offsets can occur between individual logging measurements and between different logging passes, as well as between core and log measurements. So let's take a closer look at some of these issues. In this image we can see that we have got one random data point up towards the top right of the graph. And what this is doing is it's pulling this red line, or the line of best fit, up towards it. And as a result of that, we can see that the R squared, or the number that tells us how well the line is fitting the data, is quite low at 0.2. However, if we remove that outlier, we can see that the regression improves and that we have an R squared of 0.82, and we can see that that line now fits that data much better. However, outliers should not just be removed blindly, as they can have legitimate reasons for being outliers, and further investigation would need to be carried out to understand why that point is an outlier. To evaluate the impact of machine learning models to noise, such as sensor issues or additional noise from the environment, the following case study was developed, and this focuses on the performance of a random forest regression algorithm under varying levels of normally distributed noise. The selected inputs for this were gamma ray, neutron porosity, and acoustic compressional slowness. On the right, we have the results of the prediction on the full dataset after the model was trained and validated. When noise is added to an acoustic compressional curve, we can see that the algorithm handles the noise very well, and random forest algorithms are known for being more robust to both noise and missing data compared to some other algorithms. And when pure noise is used, the algorithm still manages to follow the general trend, but it is slightly noisier. So to detect outliers, we can use a number of methods, and one of these methods is to use box plots. Here we can see some Python code on the left which allows us to generate multiple box plots for each logging curve on their own scale. The box and whiskers of the plot show where the majority of the data lies, with the ends of the whiskers being the outer limits of the data, and data beyond these limits is highlighted in green, and these are the outliers. On my channel you will find a video on box plots where I go into detail about how to interpret these box plots and how to identify outliers with them. So be sure to check that out if you're interested in learning more. So another way of identifying outliers is to use unsupervised learning techniques, and these recognize patterns within the data. So this example here uses a method known as an isolation forest and takes in several logging curves to identify potential outliers. And what you see here is the outliers on the left and the inliers, or the good data points, on the right. There is some overlap between the points, and this is due to viewing only two dimensions of the data, rho B and NumPy. As mentioned, there are several other input curves that were used in this model, and these could influence whether a point is detected as an outlier or not. Another common issue that we face is that of missing data. So to evaluate the impact of missing data, a machine learning model was developed using an artificial neural network with 4 logging curves as inputs and 1 intermediate layer with 8 neurons. The dataset was then split into training and validation subsets, with 70% of the data being used for training and 30% of the data being used for validation of the results. The validation data was kept constant to ensure a fair comparison. Once the model was validated, it was then applied to the entire dataset for final prediction. The training dataset was then reduced by 10% increments by removing random points, and then the model was retrained. So 2 metrics were then used to evaluate the performance of the model, the mean absolute error and the root mean square error. So these are common metrics used for measuring regression model performance. So in the image here, when 100% of the training data is used, the model generates a very good fit between reality and the predicted result, with an MAE of 3.28 and an RMSE of 4.457. When the training data is reduced to 50%, the model performance worsens, with RMSE and MAE both increasing. When the training data is reduced to 50%, the model performance worsens, with RMSE and MAE both increasing, and it can be seen from 3,250 meters onwards, the result fails to match the actual measurement. When the data is reduced even further to 20%, the model starts to fail completely. And at 3,240 metres, the prediction in fact goes the opposite way to reality, and both RMSE and MAE values are 3 times worse compared to when using 100% of the data. There are a few ways in Python that we can identify missing data. An example here uses matplotlib and pandas to identify where missing data values are and plots it in this handy visualization. This allows you to quickly identify where you have data and where you do not. So for example, in the well on the left we can see that DT and DTS curves are both missing, and on the right hand well we can see that they are present. However, both phi-F and SW contain a small amount of missing data. But one of my favourite libraries that is easy to use and easy to visualize missing data is the missingno library. It allows you to evaluate the pandas data frame and generate a number of plots with very easy to use commands. In this image here we have a matrix plot which shows all of the data within the data frame, and grey areas indicate where we have data and white areas indicate where the data is missing. You can also get a count of the missing values by using a bar chart, and this gives us an idea of how many values are present for each of the features or columns within the data frame. So missingno is a library that you should definitely have when you are starting to evaluate data for machine learning and carrying out exploratory data analysis. So now we'll move on to one of the most important logging curves, and that is depth. Depth is a critical measurement that allows the successful development of a well or field. It allows the setting of packers at the correct depth, and it also allows us to perforate the reservoir at the right point. All well log measurements are tied to depth, and ensuring that logging measurements are on the correct depth is a key step in the QC process and for carrying out accurate petrophysical interpretations. Offsets between logging measurements can occur for a wide variety of reasons, including differential sticking of the tool. The weight of the tool string can cause the cable to stretch, and we then end up with a difference between the logging passes. We also have different depth references between wireline and LWD. Wireline measurements rely on the logger's depth, whereas LWD measurements are tied to the driller's depth. Occasionally, incorrect pipe tallies will lead to a discrepancy between the two depth measurements, and therefore has to be investigated or corrected for. Variations in weather conditions at the surface can also cause semi-submersible rigs to move around, leading to the drill string coming off bottom and moving around. Correcting depth shifts can be done manually by picking pair points between the measurements and stretching and squeezing one of the curves to match the reference. There are a number of studies out there that have looked at automating this process, or semi-automating it, such as using dynamic time warping, which is commonly applied in signal processing. And also, machine learning models such as neural networks have been applied to do this task. So here we can split the curves out from the previous plot onto two separate plots like this. And using visual cues from both measurements we can begin a manual alignment process. We can pick easy to distinguish features on both curves. We would then work out the differences in depths between the curves and then shift the repeat pass in red to match the main pass, which is used for reference here. Another consideration when evaluating well data is the resolution and scale of the measurements. We can see here that we have a core image which can give us very granular detail, and measurements are usually made on plugs taken from the core slab. And these plugs are typically about 1 to 1.5 inches in diameter or a few centimetres in diameter. When we look at the well logging measurements, we have a wide range of vertical resolutions and depths of investigation. Density tools, for example, are relatively shallow reading with a depth of investigation of around 13 centimetres and a vertical resolution of around 20 centimetres. Other tools such as sonic tools have a much deeper depth of investigation and vertical resolution. Therefore, we do have to understand this when looking at the logging data and know that each tool could be reading different parts of the formation. So this is something that could benefit from further research into how this could impact the data and the machine learning model. So let's now move on to normalisation of gamma ray data, which is a routine part of a petrophysical workflow and can be considered controversial, with some petrophysicists preferring to apply it and others not. When we are evaluating geology within wells, it is commonly assumed that stratigraphic units within neighbouring wells should share similar properties and therefore similar log responses. However, there are often differences between the runs and between the wells that cannot be accounted for by borehole environmental predictions. Therefore, people like to apply normalisation to make the curves respond similar within similar geological units. Gamma ray normalisation should not be applied blindly, as it can remove real and important geological features. And this is where the domain expert, whether it's a petrophysicist or the geologist, can make the decision based on their domain expert knowledge. They can understand whether normalisation is appropriate or whether some features are real or not. So finally, we will now look at feature selection, and this is used to reduce the dataset to a smaller number of features by discarding ones that are irrelevant to the target feature. And this has many benefits, including improving the performance and accuracy of a machine learning algorithm, reducing the training times, especially if we are using large datasets, and it provides a better understanding of what inputs generated the final results. And methods include Pearson's correlation, backward, forward and stepwise feature elimination, and univariate feature selection. In this case study here, feature elimination was assessed on the prediction of log porosity using a neural network. And the method for choosing the variables was Pearson's correlation, which is used for measuring the strength of the relationship between two variables. This value can vary between -1 and +1, where values closer to 1 or -1 indicate a very strong relationship, and those closer to 0 indicate no relationship. All values of Pearson's were converted to absolute values, and the cutoff for Pearson's was incremented from 0.1 to 0.7. The model was then run using the features that were above this threshold, and as can be seen here, when all variables are used, the relationship between the actual measurement and the predicted measurement is poor, with a high MAE and a high RMSE. So on the scatter plot here we have the actual porosity on the x-axis and the predicted porosity on the y-axis, and we can see that the points are very scattered, are very spread out. But as we iterate through the cutoffs, the correlation starts to improve, and so too does the metrics. On this iteration we have dropped C1, C4 and the delta rho curve. At iteration 7 we are left with 3 features: bulk density, acoustic compressional and total gas or gas X. This indicates that using these 3 features would produce the best prediction result, and the presence of total gas or gas X could be an indicator of a light hydrocarbon effect, so therefore it is bringing extra information into the model, and that helps us gain better insights into our reservoir. So to summarise, the popularity of machine learning within our domain is increasing greatly, and it can have many powerful benefits in a wide range of applications. However, the data quality assurance is a time-consuming task, but a very important one. Any machine learning model that is built on poor quality data could have implications for the final model in terms of the predictive power, and also have consequences on the decisions made on the prediction results. And data issues can vary and can include missing data, as well as outliers and depth misalignment. We can then take that poor data quality and either repair it or remove it from the data, depending upon our findings from whether that data is really poor or whether it is something else. So to summarise, well-logged data and real-world data can be impacted by a variety of issues, from small issues to much larger ones. And these issues can range from outliers to missing data to offsets between the different columns or the different measurements that we have. If these issues are not identified early enough, they can have ongoing consequences in the results of that predictive model, and therefore consequences for the follow-on decisions. Therefore, it is essential that data quality and quality control of that data is considered early on as part of the machine learning workflow. And this is to ensure that good quality data is passed into the algorithm. If you want to find out more detail about the topics covered in today's video, then I've included a link in the description to my original papers that were presented last year. So be sure to give this video a thumbs up, and if you want to see more content from this channel, click on that subscribe button and ding that notification bell. So as always, thanks for watching, and until next time, bye for now.